This talk was given in the session Detection and Estimation of Sparse and Weak Signals at the Joint Statistical Meeting in August 2023 in Toronto. In a nutshell, what I'm going to show you in this talk are that existing methods for comparing the survival of two groups are generally ineffective against differences in hazard occurring in a few time instances when those instances are unknown to us in advance. And what we will do is we will try to bridge this gap. We're going to propose a method that is effective against such differences. Okay, so we're dealing here with survival analysis or survival data and its analysis. And when we think about such data, we have usually two groups. Sometimes we denote those groups as the control group or the treatment group. Here we'll call it X and Y, or the blues and the reds. Now, every group has a list of each row here is indexed by a time. It represents a time interval, and what you record is the number of at-risk patients at the beginning of your time interval, and then the number of events that you observed within this interval. Okay, some of these are called failure events or mortality events. Same thing goes with the Y group. It is common to illustrate the data using the so-called Kaplan-Meier curve, which shows a proportion of survival up until a particular time for each one of these groups. Now, it is important to note here that usually the difference between the big number of at-risk patients at the beginning and at the end of the interval equals to the number of events occurring within this interval, but this is not always the case. Okay, so for example, here we have 15 events, but altogether the difference is 16. This is because one of the patients was censored from the study, and this is something that happens quite a lot in survival data, and we want methods that can accommodate this sort of censorship. Okay, so on the Kaplan-Meier curve, usually censorship is denoted by some pluses. And the goal of the analysis altogether is to determine whether the treatment has a no-null effect. Okay, so we're comparing the two groups or the two curves, and we're trying to understand whether they represent the same mechanism or not. Now, a major tool in the analysis of survival data to determine whether there's an effect or not is called the log-rank test. Now, it's not the only test available, but many of the properties of the log-rank test also that we care about in the context of sparse signal detection also carry over to other tests. So this is why I'm going to focus at the discussion in this talk on the log-rank test. So the log-rank test or the Mantel-Cook's log-rank test was introduced by Mantel to address the issue of censorship in studies, and I'll explain now what he proposed. And what he proposes to look at every row in the survival table and then summarize things based on a table of this form. So what happens here is we look at the total number of at-risk patients denoted by capital M, and then total number of events observed within the interval by lowercase k. And now think about one event. Now, if the risk of both groups is equal at that time interval, then the event is likely to occur in either group. We only need to factor for the size of the groups. So here, the size of the group Y will be denoted by capital K, and what we'll do is we sample from a population of M items, where the ones that are colored in red are K, and we sample altogether lowercase k times. So the number of observed events, if the risk is equal in both groups, it has a hypergeometric distribution with exactly those parameters here. And what Mantel proposed was to standardize the number of observed events over the entire study using the mean and the variance of the hypergeometric distribution. And this thing has asymptotically normal, so you can get a nice test this way. Now the log rank test is good. It is first it's going to accommodate the censorship, because at each time we're looking at the total number of at-risk patients, so we can reduce from that the number of censorship events. It is also nice because it has some optimality properties under proportional hazard model. Okay, this is meaning that it's equivalent to the likelihood ratio test. So it's the equivalent to the best test in the proportional hazard model. So this is also a good reason why to use the log rank test. But in the context of our analysis, we know that the log rank test is not sensitive to excessive hazard that is localized in time. Okay, it is not built to be this way. It is built to average things over the entire duration of the study. Now, to address this fact, that someone may propose the concept of non-homogeneous log rank test. There's a family, probably more than one family of modification to the log rank test, that this is exactly their goal, trying to gain some sensitivity to effects, to differences that are perhaps more shifted toward a particular area of the study, say the beginning of the study or the end of the study, or some other pattern. Now, this perhaps can achieve this sensitivity to no proportional hazard, but it is not useful when the time interval of excessive hazard are a priori unknown to us. Okay, this is what we usually mean when we talk about sparse signal analysis. Okay, so this is the gap, and this is the gap we're trying to fill now. We're trying to attain sensitivity to excessive hazard localized in a few time instances, such that we do not know in advance where those instances might be. Now, application of this situation are perhaps many of those situations where people apply the non-homogeneous log rank test. They're actually looking for a sparse signal, but many times they did some overfitting to the data. So there's a lot of application that improved analysis can be done using the tool we're developing here on those studies. But more specifically, you can think about a situation where you're looking at survival data and you try to identify age-specific effects. Okay, so perhaps a particular factor affecting on the risk in the life of some individual, but it's only affecting at specific age or specific age groups or some intervals of the ages. So another situation, perhaps that not in the context of survival, this is in radioactive decay. So you compare the decay rate of two radioactive materials. So this situation, this radioactive material also decay also obeys the standard model of survival, and you want to understand the effect of some bursty phenomena like space weather. So this is a study that actually done in practice, trying to understand how the radioactive material in space, exposed to space weather, whether its decay is different than a radioactive material that is not exposed to the space weather. Okay, now here's the method. Okay, we call it higher criticism of hypergeometric p-values, and we showed it by HCHG. And HCHG has two steps. So first steps, we do many exact hypergeometric tests. Okay, so instead of using just mean and variance like in log rank test, what we do is we're looking at the same hypergeometric distribution as in the log rank test, but we're doing an exact test. So we get a p-value for this test. And what we'll do in step 2 is we combine all the p-values using higher criticism, because this is the formula for higher criticism. Okay, so then we use a global test applying to higher criticism. Notable properties of HCHG. So first, it can accommodate censorship the same way that log rank can. I will argue in a few slides that it is more sensitive than the log rank when instances of excessive risk are sparse and weak. And I will also mention a nice property of HCHG, that it has a built-in mechanism to identify instances of excessive risk. Okay, so what is this mechanism? So this is called higher criticism thresholding. Okay, so it's developed by Torono and Jin, and it says that if you're looking at the higher criticism objective, so higher criticism is a maximization over a particular expression, a standardized form of the p-values, and if you the maximum value gives you the higher criticism, so it is our higher criticism statistic is represented by the maximum of this curve. Now, if you look at the index that attains the maximum value, the higher criticism, usually the maximum value of the rarity curve, and you think about that as a threshold, meaning that you looking at all the p-values to the left of this curve. So this gives you a set of the smallest p-values, and this particular selection of set of p-values has some interesting optimality properties in the context of classification or detection. It gives that was discussed by Torono and Jin. Okay, so in our context, it gives us those time instances that affecting most on the change. It gives us the best evidence for change in survival between the groups. Those are the instances that are mostly suspicious of having excessive risks toward one of the groups. Okay, so now we will analyze the method under a generative model. Okay, so this is not, we're not trying to argue here that that real survival data obeys this model. This model is mostly for a sanity check and to show you that makes sense to suggest a method that is should be work as an alternative to the log rank, just because the log rank will turn out not to be useful under this model, but our method is useful. Now, although it is not, obviously, does not obey the model, this model was used before in the context of survival analysis. It is sometimes called piecewise exponential decay model. And in this model, we assume that the number of events observed every time interval has a Poisson distribution, and its rate of the Poisson is proportional to the number of at-risk patients at the beginning of the interval times some parameter which we call the hazard of that group on that interval. Okay, same thing goes with y, and for the next interval we will update the number of at-risk patients. Okay, so in this model there is no censorship, but you can incorporate censorship to the situations, not a problem. Under the null hypothesis here, the risk of every time interval is equal among the groups. Under the alternative, there is a change, but this change is sparse, meaning that for most cases, there is no change at all. Okay, we still having a lambda bar of y equal to lambda bar of x. But in some rare cases, epsilon fraction of the cases, we will have a shift. This is a shift in the Hellinger distance, and it's a shift by another parameter delta t. This delta represents the size of the effect. And what we will do is we will calibrate this whole system, so the epsilon here and the delta, such that there is a sparse and weak situation here. Okay, so this is a session of sparse and weak signal detection. So we calibrating things to have sparse and weak. Sparse meaning that the epsilon is calibrated to the time horizon t, based on this with this calibration here. So beta controls sparsity, large beta meaning sparse signal. And delta itself will also calibrate it to be small, so that the problem will be challenging. Okay, so how do we calibrate delta to be small? So it turns out that there is a nice framework to calibrate the signal such that it will bring us to a regime that is familiar to us, or at least easier to study. And this was developed by myself and with Donahoe. And this means that the framework says that what we should do is we should calibrate the model such that the p-values that we had earlier with the hypergeometric would be asymptotically approximately log chi-square distribution with over 1 degree of freedom, with a shift in the mean that is moderate. Okay, so this is what meaning moderate, meaning that it's square root of log t proportional to that. And now this particular approximation, it's made precise exactly within this paper, but this approximation gives us a blueprint on how to calibrate a model, which this model is quite complicated, especially compared to other models in the literature, because it is complicated because there is dependency here among the time instances. Okay, so the number of events at-risk patient and every time, depending on the number of events occurred in earlier times. Okay, so there is, but this tool, the log chi-square approximation that applies to batch of p-values gives us a relatively easy way out and allows us the analysis that I'll show you next. So the analysis tells us that HCHG it would be asymptotically powerful if the signal or the parameter that calibrates the signal strength is above what's the so-called phase transition curve. This is the relatively familiar phase transition curve. It is twice the sparse normal mean phase transition curve that appeared in many works before. Okay, this phase transition curve, twice the sparse normal mean ones, is actually a two-sample sparse normal means phase transition curve that Donahoe and myself derived. Now, the phase transition curve tells you that if your signal strength is above that curve, then the test statistic can be calibrated to attain a test that is its power tending to 1 while its level tends to 0. And the other regime, it tells you that no matter how you tune your test asymptotically, this test will have trivial power. The sum of type 1 plus type 2 error has to go to 1. Okay, so this is what we mean by asymptotically powerful and asymptotically powerless. Another thing that you get relatively for free because of this log chi-square approximation framework is that when beta is larger than half, so you're relatively in a very sparse area, then log rank is asymptotically powerless, and also Fisher's combination statistics of the hypergeometric p-value is asymptotically powerless. Okay, so this this result is interesting because it tells us that we're doing something right. We're proposing here a test that is better asymptotically than the log rank test. With Fisher combination statistic of hypergeometric p-value, this result, it tells you that the power or the main innovation here that we have is not because we introduced exact test instead of the normal approximation, because even if we combine those statistics in a reasonable manner, we will still not get better power asymptotically. It tells you that really the main innovation here is the introduction of the higher criticism. Okay, so this is how it looks graphically. Okay, so this is the phase transition curve of higher criticism, and here the phase transition curve of log rank, and this whole area is potentially the area where we can detect things using HCHG, but we cannot do this using log rank. So there are many discoveries here that we might do if we only applied the right tool, but we miss those discoveries, or we will miss these discoveries if we only use the classical tools. You can also see things empirically when you apply this exponential decay model. So you see that here on the left side, HCHD, so it looks like the actual phase transition, the empirical phase transition curve agrees with the theoretical one. For the log rank test, actually, there is some, it actually has some power beyond the phase transition curve. Okay, so perhaps the empirical phase transition curve may be somewhere here, but it still means that the higher criticism is much better than log rank in this area where we think, and this is a comparison that makes with simulation and compare when higher criticism of HCHG is significantly better than log rank, and we get this picture here. Okay, so it's definitely better to use HCHG for very sparse signals. So the last part of the talk, what I want to do is to demonstrate how to use it for real gene expression data. Okay, so it's not want to argue here that we about the scientific value of the analysis we're doing. It's mostly to demonstrate the use cases and the kind of signals that HCHG can detect. So for doing that, we will use a data set of about 3,000 breast cancer patients, and each patient had its expression level over about 8,700 genes. And what we will do in order to get survival data to compare groups, we take every gene, and every gene gives us an assignment of the patients in the two groups. How do we assign them? We take the median value of the expression of this gene, and we look at patients whose median value is higher than the median, whose value is higher than the median. This is going to be those comprise group Y, and those that are lower will comprise group X. We also, another thing that we did is we consolidated the events into 21-day interval, okay, instead of just individual days. Okay, there are some reason why we do it here, and we discussed that in the paper. So here is an example for the gene. This is the gene named ADSS, and there is this group are the group of the individuals with expression value for this gene, which is lower than the median, and Y group is of those that are higher than the median. Now we applied our test, and we also applied log rank. Then we we see that we can record how many discoveries each one reported. Okay, so how many genes with expression level that is significantly associated with survival, according to either HCHG or log rank. So log rank did discover perhaps many more genes. There's also quite a big area of overlap, but most interestingly, there is here on the side, there are about 430 genes that were discovered by HCHG, but are completely missed by the log rank. And you can here is a table, gives you 10 of those genes. Okay, so here we included here the p-value of the higher criticism test. Okay, so not the p-value of the individual row in the survival, but we translate the HC value to a test. Same thing we did with the log rank, and this shows you that those genes were reported significantly associated with survival by HC and not by log rank. You can also look at some of those genes like this, like ADSS. So here are the survival curves. This thing was found to be significant by higher criticism, but insignificant by the log rank, at least at the 0.05 level. And what you see at the bottom here are those time instances that that were reported by the higher criticism thresholds. Okay, so you can see that those instances are definitely associated with very small p-values, and the higher criticism threshold thinks that those are important points to look at. Okay, potentially there are other points that can witness difference, but those were reported by HC threshold. And you can see similar pictures to other genes. Okay, here's another gene with some other potential values, and then another one. Okay, with this I will summarize the talk. HCAG, the method we are proposing, is based on many exact hypergeometric tests. And then global testing with higher criticism. As a bonus step, you can also include here the use of higher criticism thresholding to identify instances or intervals of excessive risk. HCHG is sensitive to sparse and weak deviations of non-proportional hazard. And I showed you that this theoretically, we showed that it's more powerful than existing methods in exponential decay, sparse and weak hazard departure setting. Okay, so that was the theoretic generative model that we looked at. We also showed that empirically, we find many discoveries that are not reported by the log rank test. With that, I will finish the talk. Our paper will be available in arXiv within a few days. Thank you.